David Smith here with one more flipped classroom math video. 3 tips before we start. First, remember that you can slow down or speed up playback if that helps you follow along. Second, you could turn on the captions and watch my words go by on the bottom of the screen. And lastly, you can pause the video at any time to catch up with your notes or think about the topic. Today's video is one of 2 review videos for our probability unit. Now this review is going to closely follow the Oxford University textbook Chapter 7 for the IB Diploma program. However, chances are really good that this stuff is useful and helpful for anybody studying probability. So the first video is just going to be what I'm calling sort of straight up probability calculations, where we have events, probabilities are known, things like that. We'll calculate probability. The second video is going to cover random variables and probability distributions. There's enough in Chapter 7 that I thought it'd be better to do 2 parts because they kind of organize pretty well in that way. So let's take a look. Lesson 7a was mostly about vocabulary. We had event, trials, outcomes, and sample space. You're going to want to know what all of these mean. And then we had experimental versus theoretical probability. Now, theoretical is if you roll a die and it's a fair die, you know that any one number has a 1/6 chance of coming up. That's theoretical probability. Experimental would be if we have a rock that's got sides, but it's really not regularly shaped, so we can't say just by looking at it what the probability that one side is that it will come up. So what we do is we throw that rock a million times, count up all the different outcomes, and figure out the probability based on those experiments. Okay, some quick notation. The probability of A, P of event A, is this fraction. The number of outcomes that correspond to A and the total number of outcomes in the sample space. So for example, if we're calculating the probability of rolling a 6 on a die, the number of 6s in the sample space is just 1. There's only one face with a 6, and there's a total of 6 outcomes. So the probability is 1/6. 7b covers expected outcomes. And this is very closely tied into 7a. In fact, in my class, we just combined those 2 lessons into one section. So expected number of outcomes for multiple trials. So let's go back to that dice rolling. What if I roll a dice 23 times? How many 6s would we expect? And we have a pretty straightforward formula for that. Expected variable x is just the number of trials times the probability. So expected number of 6s for 23 rolls is just going to be 23 times 1/6. And this gives us an expected number of 6s in 23 rolls as 3.8 6s. Now, of course, if we roll 23 times, we can't get 6.8 6s. We're going to get a whole number, an integer for that. So don't let that trip you up. Expected values usually have decimal places and they don't line up perfectly with what you might be expecting from reality. Lesson 7c introduced Venn diagrams, which we continue to use throughout this straight up probability section. So to make a Venn diagram, you might be given something like this, and then you're asked to create that Venn diagram, and then you're going to be asked some probability questions based on the Venn diagram. So if you'd like a little practice, go ahead and use this information to make a Venn diagram. Okay, here's my Venn diagram. Now this example was a straightforward one. You didn't need to actually figure anything out. You could just start by putting your 4 that like both, and then this means that the aardvarks need to be 6 because together they make 10. And that the armadillos alone need to be 8 because they have to add up to 12. And then 2 is neither. That comes straight off the prompt. And then we'll add them all up, and we know we have 20 total. Now you're going to be asked to do probabilities based on the Venn diagram. So let's do one right away. What's the probability that someone likes armadillos but not aardvarks? Go ahead, pause the video, see if you can come up with that fraction. Okay, let's just do one more on this. You'll recall we did a lot of variations on these kinds of prompts. So here's a prompt. What's the probability that someone likes aardvarks given that they like armadillos? So pause the video for a sec, see if you can figure out that fraction. Okay, the key to that is that the given that is the bottom of your fraction. So given that they like armadillos, there's 12 people that like armadillos. And then how many of those people like aardvarks? There's 4. So that gives us a 4 out of 12. Now, as you'll recall, we had some more complicated Venn diagrams. We had 3-way Venn diagrams. And these are diagrams that show situations where there's actually 3 things that we're keeping track of. Could be like dogs, cats, and birds. It could be a number of things. Now, in our class, we saw 2 types of these. We saw this type of Venn diagram where there's no overlap between all 3. There's just an overlap between these 2 and then an overlap between these 2. And then we had a Venn diagram where there's an overlap between all 3. And what that means is that this region right in the middle satisfies the conditions for all 3 of the groups that we have. Another really handy way to find probabilities is to organize your outcomes in a table. And in this case, it's going to be helpful to do that. So we have 2 dice. They're 4-sided dice. They're fair dice. And one of them has 1, 2, 3, 4 on it, and the other one has 3, 4, 5, 6. We roll both dice, and the outcome is the sum. So pause the video and make a quick little table based on this scenario. Action. So very quickly, there's my table. You don't have to get all formal and fancy and box it all in. This will do fine. If you're being really thorough, you'd write dice number 2 maybe and dice number 1 here, but pretty much I can see what you're doing with that. And now, inside my table, I wrote the sum. So adding 1 and 3 gives me a 4, and so on for every one of these. Now pay attention, these problems are tricky. They might say product instead of sum, in which case you'd have to multiply both of these to get your outcomes. So now, here is a probability type question you might get. What's the probability that the sum, and we're going to say x is greater than or equal to 7? So go ahead, pause the video, figure that out. Okay, just one example of how we might calculate with that. What I did here is kind of nice. I just circled the probabilities that meet our criteria, greater than or equal to 7, and I counted them up. There's 10 in there, 16 total, so the probability is 10 over 16. Apologies, I didn't update the letter for the last board. That was 7D. Now we're on 7E. Now, we have a bunch of different ways to show sample space, to show probabilistic situations. So choosing a diagram is an important skill to have. You might get a probability question that's just expressed in words, and making the right kind of diagram without a prompt is going to help you answer the probability question. So let's check this out. We had tables, lists, and Venn diagrams. Later we're going to get to probability trees. Tables are mostly more simple. They combine 2 events, like flipping a coin and rolling a die, and then recording heads and the number, and so you make a nice table for that one. Lists are even more simple. This would be like flipping a coin twice and just listing all the possible outcomes. So that would be like, we could have a heads, 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 tails, tails, heads, and tails, tails. And for 2 flips of a coin, writing the list is pretty simple. But if we had 4 flips or 6 flips, it gets pretty complicated. And we handle that a little later when we talk about the binomial distribution. But in the straight up probability section, we don't go that far. So don't make a list if your situation is complex. And then lastly, we had Venn diagrams. These are the most complex. The one basic way to get your head around this is there's multiple ways to satisfy one condition. Or we have like 3 conditions. Like people shop at Bash's', they shop at Safeway, or they shop at Costco. Or they shop at all 3 or any 2 together or none. That's going to be best handled with a Venn diagram. All right, we're going to talk about combined events. That was lesson 7F. There's a bunch of symbols you need to understand to answer the questions. So we're going to start with 3: intersection, union, and the not, the complement. So the intersection is more restrictive. It wants elements that are in both situations or sets. We're calling them sets. They're sets of outcomes. So the intersection means whatever you're looking at has to be both in the 2 or 3 sets that we're looking at. So intersection is and. The U, the right side up one, is union. And this can be in either set. So again, if we're comparing 2 sets, the union is everything that's in A plus everything that's in B plus everything that's in both of them. So that would be the union, and that's less restrictive. That's or. Finally, we have this little dash, this little single accent mark, single quote, and that means complement. And it's just everything that's not in set A. Okay, so if set A has all these items and then there are other items in the whole sample space, then the complement of A is all those other items that are not in A. Okay, one last symbol and then we'll do just a few problems here. So this vertical line is sort of the given that. It's a conditional probability. The way you read this is what is the probability of A happening given that our event already satisfies the condition of B. So again, we're doing combined events. So this one is the most tricky. It comes up later, comes up all throughout chapter 7, and you need to know how to interpret this prompt and then apply the correct formula. So conditional, probability A given already in B, and the kind of English quote is given that. Okay, I'm going to use a Venn diagram to put together some probability prompts. This is by no means all of the prompts that you might get, but this will give you a feel for what we're doing. So your first one, what is the probability of event A happening? So the first thing we need is we need the total of all of the outcomes here. So I added these all up, and our total is 45. Okay? So now, probability of A happening in this whole sample space is just going to be all the numbers that are part of A. So we have 5, that makes 11, plus 12 is 23. So this would be 23 over 45. Now the second one, probability of A happening given that C already happened, that would be all of the C's. So we have 2 plus 6 makes 8, plus 3 makes 11, plus 9 equals 20. So that's the bottom. That's given that C happened. And then we need all the A's that are in C happening. And that would be these, the 6 and the 9. The 6 and the 3, which makes 9 out of 20. Figure out the probability that's not in A. Okay, so what I did there is I just added up all the things that aren't in the A circle. So none of these qualify because they are in A, even though they're also in B and C. Now, there's another way to do this one. A and not A together have to add up to 1, because in any situation, the not, it's called the complement because with A and the complement of A, you get to 1. And you can see here, probability of A is 23 over 45, probability of not A is 22 over 45. Together that makes 45 out of 45. So, figure out the probability of A union B, A or B. All right, I just added up everything that's in A and B, and a quick way to do that is just add up the things that are not in A and B, and that's 2 and 3. So subtract that 5 from 45, and I get 40 over 45 for A union B. Now, do A intersection B, and we'll be done. Okay, the intersection of A and B is just these two here, so that's 5 out of our total outcomes is 45. Okay, in the next lesson, 7G, we talked about 3 types of events. We have mutually exclusive events, we have independent events, and we have dependent events. Now, mutually exclusive are things that can't happen together. Like, for example, if I roll a die one time, I can't get a 6 and a 4 with one roll, okay? Just can't happen, okay? So that's an example of a mutually exclusive event. Independent events are events that don't affect each other. So let's say I pick a student at random from a group of high school students, and the first event I'm selecting for is, do I have a boy or a girl? And then the second event is, are they brown-haired or blonde? So it doesn't matter whether it's a boy or a girl, the probability is going to be the same in terms of their hair color. So these would be independent events. Now maybe there's something about biology there that would change that, but we're just assuming that boys and girls are equally likely to be brown hair or blonde hair. So those two would be independent. The chance of getting a blonde doesn't matter whether you got a girl or a boy first. Okay, so those would be independent events. Now dependent events are events that depend on each other. So let's say I have two draws from a deck of cards with no replacement. So I draw one card, keep that, draw a second card, and keep that. And I'm trying to figure out the probability of, say, drawing a 6 each time. Now the first time, it's going to be 4 out of 52. That's going to be my probability of getting a 6. But the second time, it's going to be 3 out of 51. So those two events are dependent on each other for probability. Okay, now that we've talked about event types, let's talk about the rules and how they apply and can be used with various event types. Now, I'm not going to do a bunch of examples because that would make this video way too long. There's links in the comments below to all the individual lesson videos that are covered in this first part of Chapter 7. So if you want some review, you should take a look at some of those. So here we go. All events, I don't care which type of event, the probability of A given that B happened is just going to be the probability of the intersection of A and B over the probability of B. So that's for every single event. That equation holds true. Now additionally, if we know they're independent, then the intersection is just going to be the probability of A times the probability of B. Sweet, okay? And then that tells us also, remember, independent events, the probability of A shouldn't change depending on whether or not B happened. So that means that the probability of A given B should just be the probability of A. And you can use these two equations here to prove that symbolically if you want. Finally, or not finally, almost finally, we have mutually exclusive events. Now what that means is that there is no intersection. Both events cannot happen at the same time, so the probability of the intersection is 0. Sweet, that's good. And so by inference or by deduction, dependent events, the probability of the intersection has to be greater than 0. In other words, you have to have an intersection if they're independent or dependent. The last lesson in our first section on probability was 7H, and here we use probability trees to analyze complicated situations. So to be specific, these are helpful for situations with multiple dependent events. So for example, the first pick affects the odds of the next pick. So let's do an example. Okay, here's our one probability tree example in this video. Check this out. We're going to draw 3 cards from a deck of standard playing cards. Now what we want is a tree that will help us calculate the probability of drawing hearts. So in each draw, we're going to record whether we got a heart or not. So if you want, if you're feeling bold, pause the video right now and see if you can make that tree. We have 3 draws. Okay, I hope you realized that we're not tracking all the suits. We're just tracking whether we got a heart or not. So we don't need to track spades, clubs, and diamonds. We could, and that tree would work, and it would let us calculate probabilities of various combinations of hearts. But it'd be way more complicated, harder to draw, and you can see I've already I ran out of space. I had to smush my third draw down in there a little bit, but it's okay, we're good. So now you can use this tree to calculate whatever probabilities you want. So if you're feeling bold, pause the video and put your probabilities on each branch. Okay, I went ahead and did that. I'm not going to go over every number, but I am going to point out some key things. So every branch, like there's a branching, here's a branching, every time it branches, the probabilities have to add up to 1. So you can see here in our first branch, 13 plus 39 is 52, so that's 52 over 52. Back here at our third branch, out here, we've got 12 out of 50 and 38 out of 50, which adds up to 50 out of 50. So that you have to do. Now, a real simple one is what is the probability of getting 3 hearts? You would just multiply the first heart probability times the second heart probability times the third heart probability. So that would be 13 over 52 times 12 over 51 times 11 over 50. And that's going to be a pretty small number. Okay, now I want you to do a more complicated probability calculation. Let's do at least 2 hearts, okay? So identify the branches of the tree that you're going to have to calculate. Okay, so check this out. I starred every outcome where we have at least 2 hearts. So this one is 3 hearts. This one is 2 hearts. So is this one. This is a heart, no heart, but then a heart. So that one's 2 hearts. And then finally we have no heart, heart, heart. So that's the 4th one. So what we would do is we'd multiply to get the probabilities here, figure those out, multiply those fractions together, and then add all those up for the total probability. So the key is to figure out the probability of a branch, you multiply. To figure out the total probability of any situation where there's multiple branches, you add those probabilities up for the total. Now that you've watched the video, jot down a couple notes so you can ask questions at our next class. Remember that you can also watch the video again just to deepen your understanding. Lastly, if you enjoyed the video, please click like and subscribe.